Hello, thank you very much. Can you hear me and see my screen properly? Okay, thank you. Yeah, I'll be presenting the paper titled Independent Channel Design Approach for Stability Analysis of Grid-Connected Converters. I wanted to mention that this project is funded by SolarAirNet. The project is called Development of Tools for Effective Control of Large PV Power Plants. So this is the content of my presentation. I will start with an introduction, and then I will introduce the approach I'm trying to do in this work, and I'll perform some analysis utilizing this approach, and I'll finalize the presentation with the conclusions of the work. We've had control interactions reported in the literature. They are called usually harmonic instability, and these issues have been reported in offshore wind farms and HVDC systems as well. And you can also find material for solar PV plants as well in some cases. And the question is, what tools do we have to study this phenomena? We have eigenvalue analysis, but the disadvantage with this is that we need to have details of every component of the system, which can be a limitation if you want to model the converter due to intellectual property issues. Then we have frequency domain analysis, which is claimed to be I mean, you can, for example, get the characteristics of the converter by a frequency sweep if you get a black box model. So in that case, it's very helpful. You can then utilize the passivity-based analysis, Nyquist stability criterion. But the issue with this tools is that when you have a single input, single output system, the passivity-based analysis, for example, gives you a physical interpretation actually of the phenomena that takes place. So, for example, if you have a resonance in the grid, and if you show that the converter is non-passive, which could be interpreted as if the converter is acting as a negative resistance, you could say that okay, the resonance finds a negative resistance, and then that is why we have a resonance amplification. But when you have a multiple input, multiple output system, this is actually more difficult to see. In this case, the converter is it's a three-phase system that can be further reduced to a two-phase system in the DQ frame, for example. So we'll have a two input, two output system in this case. So the problem becomes complex, and this is actually the aim of this work, to try to reduce the complexity of studying a MIMO system, multiple input, multiple output system, by studying two single input, single output systems, so we can give a physical interpretation of the phenomena we find. To start, we did a preliminary study. It's a simulation where we have a converter connected to a grid. The grid has a short circuit ratio of 2, and we have a cable in between. And the converter controls the voltage on the DC side and the voltage in the AC side. And in the DC side, we have a current source that could be, for example, a solar panel that push power into the AC grid. We have a vector current controller in the converter, and the speed of the controllers, the controller parameters are tuned as recommended in the literature. We did two tests. We increased the power from -1 to +1. Minus is power going into the converter, and positive means power injected into the AC source. So we increased the power in this way, and we tested two cable lengths. We have a cable length of 20 kilometers and another cable length of 32 kilometers. And we see that in the first case, with the cable length of 20 kilometers, there is no instability. The new operating point is reached without any problems. But when we have a longer cable length, we see that there are growing oscillations in the simulation, and we can see if we look at the poles of the system, we can see that the poles become we get unstable poles when the power is higher than minus 0.5 per unit, and the resonance frequency is about 52.6 hertz. So the question is, what triggers instability? What is the phenomena here going on, and what is the participation of each subsystem into the instability mechanism? So this is where where I thought the independent channel design approach could be of help. The main idea is that it allows you to reduce the analysis of a two input to output system, for example, of this form, for example, with where you have a diagonal controller, and you should be you are able to simplify to represent this this system as these two single input, single output systems. So the stability then can be determined, instead of using this whole loop, the stability of the system can be determined by looking into the stability of the individual channels. They are not completely independent. The impact of each channel into the other can be seen in these two terms, gamma H2 and gamma H1. So we have the impact of say channel 2 into channel 1 given by this term. The way we can use this in our system is like this. I mean, we can split the system at the point where the converter is connected, and on this side, on one side we'll have the converter admittance, and on the other side we can have the AC grid impedance. And if we work in the sequence domain, we can show that the grid impedance is a diagonal system. Actually, the grid matrix is a diagonal matrix, and this has exactly the form of the where the independent channel design can be approach can be applied. In this case, we can have two channels. We call the first channel the positive sequence channel, because it is where we have the positive sequence terms mostly dominating the system. And the other channel, we call it negative sequence channel. We have the coupling terms here, gamma Hn and gamma gamma Hp. So if we would like to further simplify these two channels, then the question will be, will there be any case where the coupling terms can be neglected, especially in cases where we are interested in resonance-related questions, for example? So this is what we're going to see in the next analysis. So this is a plot of the this is the Nyquist plot of the two open loop channels for different power injections. We have here the positive sequence channels defined by CP, and this is defined by this expression. And we have the plots for the power injections of -1, 0, and +1, and we see that when the power injections are +1 and 0, they enclose the point -1, indicating that the system is unstable. And we see that when the power injection is -1, the Nyquist plot doesn't enclose the point -1, and this coincides with the conclusion we got from the pole analysis, where we said that the instability takes place when we have a power injection higher than -0.5. So we have instability here for 0 and +1. And when we look at the negative sequence channels, we see that for all the cases, the encirclement is far from enclosing the point -1. We should mention also that the positive sequence encirclement occurs for frequencies between 1 per unit. In this case, the base is 50 Hertz and 2.5 per unit. And the negative sequence encirclement occurs at frequencies between 2.5 and 4.5. Okay. So yeah, we wanted to see if we can further simplify the channels by neglecting the coupling terms. And we have plotted then these terms gamma HN and gamma HP. And for the positive sequence frequency of range of interest, we said that we are interested in the frequency range of +1 to 2.5, and we can see that this term is actually very small for this frequency range of interest. So this means that this channel can actually be represented or can be approximated by this instead of the larger expression we had before. And for the negative sequence frequency range of interest, which is between 2.5 and 4 per unit, we see that the term gamma HP is small as well, which allows us to represent, to approximate the negative sequence channel as shown in this figure. So what we can see in this case is that these two channels are then completely independent. We only have positive sequence terms in the positive sequence channel, and we have negative sequence terms in the negative sequence channel. But these are only if we are interested in studying resonance-related questions. So this is a comparison between the approximated channels with the complete channels, and we can see, for example, for the case where we have instability, that the positive sequence channel follows, the approximated expression follows closely the complete expression, and also for the negative sequence channel. One thing I didn't mention also is that we can say also that the instability originated, the instability is originated in the positive sequence channel rather than negative sequence channel. So that will be one conclusion of the work. So how can we use then the independent channel design? I mean, or I would say, what is the advantage? In this case, we can use, for example, the passivity-based approach. So in this case, we have the real part of the converter admittance, which will be a conductance for the positive sequence channel for powers of +1 and -1. And when the converter is injecting power, we see that there is a negative conductance region. And when the converter is consuming power, we see that this region actually decreases quite a lot. And we can plot together also the resonances when we have 20 kilometers and we have 32 kilometers. When you have 20 kilometers, the resonance coincides with actually a positive conductance, which means that the resonance will be dissipated in the converter. But when we have a 32 kilometer cable, we see that the resonance coincides with a negative conductance region when the converter is injecting 1 per unit, which means that the resonance will, or there is a risk that the resonance becomes amplified. When we look at the negative sequence channel, we can see that for both power injections, we see that the resonances coincide with a positive conductance. And hence, we can see that why the negative sequence channel didn't have very high risk of introducing instability on the system. Okay, so how valid is this approach? I mean, this approach has been shown in this paper for a particular case, and yeah, the idea was to do a first exploration. But I would say that the approach could be, it has some generality form, I would say, because all the analysis has been done in per unit. thus the shape of gamma, which is mostly dependent on the converter parameters, should have the same shape, even if we have different rated values for voltages or powers. Gamma would change if, for example, we change the speed of the converters. And actually, this term gamma is the one that mostly decides whether the negative sequence channels will have a strong impact, a strong influence in the positive sequence channel. This term is also expected to be low, the term Hn for the positive for the positive sequence channel sequence channel frequency range of interest. So then we can say that there will be small impact from the negative sequence channel in the positive sequence channel.
Oh, 2 minutes.
Sorry?
2 minutes, please.
Okay, yeah. Then the approximation, if we increase the length of the cable, then we can see actually that the approach is not valid. So this is an example where we have that the encirclement closes in both channels, but we have the resonance-related encirclements far away from this. So we should be careful if we have. I mean, we should be careful in all the cases. We should. When it comes to resonance-related questions, then I think the approach can be used to study stability of the system. But for stabilities of other natures, then the approach will not be applicable, I would say. So the conclusions is the first one is that we show that we can have positive and negative frequency channels, and that the coupling terms can be neglected. We have further simplified the channels, and we see that we can use, for example, tools like passivity-based analysis in CISO systems. The instability takes mostly due to the interaction of the positive sequence channels, but the risk is lower in the negative sequence channel. And the proposed simplification and approach can be used to study AC grid resonances related instabilities. For other instability types, the full expressions should be used. Thank you very much for your attention.
Thank you very much, Gustavo. So we have already 2 questions. I'm going to read them. So the first one is from Joachim Björk. Have you considered studying the coupling in the 2 input, 2 output system using the relative gain array?
I know about that approach, but honestly, I didn't look in detail there. But yeah, it could be, I think, a good comparison to see if we see still if we still see that interactions could be identified between the channels through the relative gain array. Yeah, I think it's a good suggestion.
Food for thoughts. Thank you, Joachim. Second question is from Andrei Gorbunov. The suggested input channels that decouple the system are linear combination of the original inputs that are physical parameters such as frequency, voltage, etc. Thus, the suggested control is not autonomous anymore. Is that right?
Oh, it was a difficult question to grasp. What does it mean to be autonomous?
Well, Andrei is raising his hand. Andrei, you can talk now.
Yeah, can you hear me?
Yes.
Yeah, thank you. I think it will be faster. Thank you for presentation. I mean, just before each inverter have its own controls. That means each inverter. Could you go to the second slide when you show the control structure? Each inverter have a local measurements, right? And then it's adjusted its references according to the local measurements. Now,
yes.
Yeah, your inputs is ER, UR, right? And this is for only one inverter.
Yes.
So if we have the interconnection of multiple inverters and you suggested some new scheme that decouple the control, that new channels will be the combinations of these inputs. And this means each inverter to use your control, each inverter should take the measurements not of the local, not of this current bus, but the measurements of its neighbors, right?
Yeah. Okay. Yeah. That's that's a question going beyond. Yeah. You say that if we would like to decouple the operation of each inverter from each other, we need information from the other inverters.
This is what I mean.
Yeah.
Exactly.
Yeah. I mean, I haven't looked into that problem actually, but yes, I think yes. If you would like to get an independent controller from other from the other inverters, for example, yeah, you definitely will need information of the from the others what they are seeing and things like that.
Yeah, thank you. My question was about that, because in this case you need to have the communication infrastructure.
Yeah,
that is not kind of then need to be addressed. Probably we don't have that. Yeah, thank you very much.
Thank you, Andrei. I'm gonna mute you.